In this video, we're going to take a look at the mole, how the mole relates to mass, and how the mole also relates to the volume of a gas. For the mole-mass relationship, as we already have discussed, it is just the molar mass. The molar mass of any substance is how many grams there are of that substance in 1 mole of that substance. So we can use that molar mass again as a conversion factor, because if they are equal to each other, then setting them as a fraction over each other would therefore equal 1 and not change the overall value, allowing us to, again, change units from one set of units to a different set of units without changing its overall value. We just need to make sure we're careful with the diatomic elements, because when you're given just oxygen, it's assumed that it is O2, elemental oxygen, so you're not going to use just that 16 grams of the atomic mass of oxygen, but actually 32 for the diatomic molecule of oxygen. So to be able to convert between moles and mass, you need, again, the molar mass, and you're going to use it in a way that will allow you to reduce out the units that you have, getting you to units that you want. So in order to solve for mass, we're going to put the molar mass on top with the mole on the bottom, therefore taking the number of moles that you're starting with and reducing them out when it's divided by itself, leaving you with grams, and therefore able to solve for how many grams you would have. You can also use the reciprocal once again, because if now I have mass and I'm trying to get to moles, if I use it the other way around, it's still going to equal 1, but now it's going to take the grams that I have to start, and they will reduce out and get me to moles, rather than, as we saw above, where they're going to reduce out moles and leave us with grams. So let's take a look at what each one of those type of problems would look like. We'll start off with going from moles to grams. So we're going to take a look at aluminum, and aluminum, as it oxidizes, gives a protective coating, so it's used often in satellites because it's not going to flake away like iron does, and it's also very lightweight. So this satellite is coated in aluminum, it's oxidized on the outside, and we find there to be 9.45 moles of aluminum oxide that is coating the outside of the satellite. Well, what is the mass of that 9.45 moles of aluminum oxide? So we're going to analyze this problem, list out what we know, what we don't know, and we know we're trying to find the grams of aluminum oxide. We know how many moles we have to start, 9.45 moles of aluminum oxide. So how can we relate the moles that we have to the grams that we want? What units we have to what units we're trying to get to. We know that the relationship between moles and mass is the molar mass. So to find the molar mass, again, take the number of atoms of each element within that compound times the molar mass of each element, then take the sum of them. We find aluminum oxide has a molar mass of 102 grams per mole. So to make it a little bit easier for us going down the road, we'll just split that into an inequality. So 1 mole of aluminum oxide equals 102 grams of aluminum oxide, because as it's written with 102 grams per mole, well, that already puts grams on top and moles on the bottom. So if we just change it into an equality, then we can make it fit into our equation a little bit more easily, however we want, however it's going to get us to the units that we need. So now we'll take our given, put it over 1. So we're trying to get to grams of aluminum oxide, take our 9.45 moles of aluminum oxide that we're going to start with, again putting it over 1, making a fraction out of it, because we are going to multiply it by a conversion factor, by another fraction. We don't want to accidentally end up putting it on the bottom when it's really on the top. So now I need to set up my conversion factor in a way again so that we could reduce out our moles and get us to grams. And the 102 grams per mole actually works out this time, but going the other direction, we'd want to flip it. So again, that's why we made the equality of it. So putting moles on the bottom to make the moles reduce out, leave me with grams, which we have on top. And that now, again, is the unit I'm looking for. I'm trying to find grams of aluminum oxide. So since the grams that I have now match the grams I'm trying to find, I know I've reached the end, and I can just calculate out and find that there are 964 grams of aluminum oxide in that 9.45 moles of aluminum oxide. Now let's take a look at it going the other direction. So now if I have grams I'm trying to get to moles, it's going to be the same relationship, but again, we're going to use the inverse this time. So looking at iron as it rusts, it goes from iron to iron 3 oxide. Well, if I have 92.2 grams of iron 3 oxide, or rust, that is formed, how many moles is that? So again, listing out known and unknown, I'm trying to find how many moles, and I know that I'm starting with that 92.2 grams of rust. So now again, I have to ask myself, how do my grams of rust relate to my moles of rust? Again, grams and moles is molar mass. So I need to find the molar mass of iron 3 oxide. So 2 atoms of iron times the 55.8 atomic mass of iron, 111.6, plus the 3 atoms of oxygen times the molar mass of oxygen, 16, gives us 48. Add those together and we find that iron 3 oxide, or rust, has a molar mass of 159.6 grams per mole. But again, let's change that into an equality. That way it'll be a little bit easier to manipulate later on. So there are 159.6 grams of iron 3 oxide in 1 mole of iron 3 oxide. Now I'm going to start the same process, given over 1. So I'm trying to solve for those grams of iron 3 oxide, and I'm starting with that 92.2 grams of iron 3 oxide, putting that over 1. And now using that equality to make my conversion factor in a way that's going to reduce out the grams that I have, getting me to a much more useful unit, which happens to be the unit that I want, those moles of iron 3 oxide. So grams of iron 3 oxide reduce out, leave me with those moles. So now I can just calculate, and I find there to be 0.578 moles of the iron 3 oxide for that 92.2 grams of iron 3 oxide that was formed. So now let's take a look at how the mole relates to volume. So when we talk about moles and volume, we're only talking about gases. We can't relate solids and liquids to their volume with moles, but gases, as Avogadro noticed, you would have the same amount of gas no matter what its molar mass is for the same set of conditions of volume and temperature and pressure. Therefore, it had the same amount of particles, that 6.02 times 10 to the 23rd particles for every mole. So at any set of conditions, as long as we have the same set of conditions for these different gases, it is the same amount. And we're going to use the standard temperature and pressure for our volume, which is 1 atmosphere pressure at 0 degrees Celsius. Then we're going to have 22.4 liters of that gas for 1 mole. So the volume of gas we can find using that relationship, again as a conversion factor, since they're equal to each other. I can take the moles that I have, multiply by that 22.4 liters for every 1 mole, making moles reduce out, leaving me with the volume in liters that I'm looking for. And again, I can use the inverse of it to also then get the other direction. If I have volume and I'm trying to get to moles, I can use that 1 mole over 22.4 liters. Now the volume reduces out, leaving me with moles of gas. I can also use this with density. So I can relate the density of a gas to its molar mass, again because density is grams per liter, grams per volume. And then if I multiply by that 22.4 liters over 1 mole, now I have liters on the bottom of my first fraction with liters on top of my second fraction. Again, they're going to reduce out, leaving me with grams per mole, which is the unit for my molar mass. So let's take a look at what each one of these type of problems would look like. So here I have a problem where as coal is burning, sulfur dioxide gas is being produced. So I want to know what volume of sulfur dioxide gas is being produced if there are 0.6 moles of sulfur dioxide that are formed. So let's take a look at what we know and what we don't know. Again, what is the volume? We're trying to find the liters of sulfur dioxide gas that is being produced when our 0.6 moles of sulfur dioxide gas is what is being produced. So the relationship between moles and liters, between my known and my unknown units, is that 22.4 liters of sulfur dioxide gas is 1 mole of sulfur dioxide gas. Again, at standard temperature and pressure. So I'm going to take my 0.6 moles of sulfur dioxide gas, my given, put it over 1, and use that equivalency up there in my known between moles and liters that will allow me to reduce out moles and get 2 liters. So I need that 1 mole of sulfur dioxide gas on the bottom and the 22.4 liters of sulfur dioxide gas on top. Because moles divided by moles, again, reduces out, leaving me with liters, and I am trying to solve for liters, so now I know I'm at the end of this problem, and I can just calculate out that there are 13.4 liters of sulfur dioxide gas that are produced as that 0.6 moles of sulfur dioxide gas is being produced. And again, we can use that same relationship going the other direction. If we were given liters to start, we could have put the 22.4 liters on the bottom and then put moles on top. So let's take a look at how molar mass and density can be related. So I have a gas that's made up of carbon and oxygen. The tough thing with carbon and oxygen is we don't know what its makeup is. I can't find its molar mass just from adding together carbon and oxygen because we know carbon and oxygen get together in a 1:1 and a 1:2 ratio, carbon monoxide and carbon dioxide. But I do have its density, and from the density I can get to its molar mass to then determine which type of carbon-oxygen gas this is. So let's list out our known and unknown once again. Again, we're trying to find the molar mass, how many grams per mole, and we're trying to then use the grams per liter or the density that we're given. So rather than writing in grams per liter, we'll change it to a fraction, make it a little bit easier to use later on, that 1.964 grams over 1 liter. And since I have grams per liter, I'm trying to grams per mole. I know I don't want the unit liter on the bottom. I want the unit mole on the bottom. And how could I change out liters for moles? Again, that molar volume. 1 mole of a gas is 22.4 liters of a gas. So now I can take, again, my given, but I don't need to really put it over 1 because it kind of already is over 1 in the relationship that is given to us. 1.964 grams per 1 liter, that is its density. But now, again, normally we're putting down on the bottom the unit we're trying to get rid of. Normally that grams that's up top on the numerator of our first fraction is what we're trying to reduce out. But this time, actually, it's that liters on the bottom of that first fraction that we don't want. So I need liters on top of my second fraction. So I want 22.4 liters on top of that 1 mole. That's how I'm going to use that relationship this time. So now, again, liters divided by liters still will reduce out. Now I'm left with grams divided by moles, which is the unit for molar mass. So I can solve this out, and I find that it is 44 grams per mole for this given gas of carbon and oxygen. Since carbon has a mass of 12, oxygen mass is 16, well, 12 plus 16 is 28, so carbon monoxide would have a molar mass of only 28 grams per mole. So we can deduct this as carbon dioxide. So 2 oxygens, 32, plus the other 12, 44. And so from the density of that 44 grams per mole, now I know which type of gas this is.